There's two different types of theory on quantum computing. There's the theory of what we would do if we had a quantum computer, and then there's the theory on how do we actually go about making a quantum computer.
In quantum computing, it's a little different. What happens is you're really taking advantage of the basic quantum behavior of a system, and what's been realized is that you can actually take advantage of this behavior to compute certain kinds of things. Say 1,000-digit decimal digit number, it would probably take all the existing computers the age of the universe to factor that number. Whereas a quantum computer of appropriate size can do it in an hour. It turns out that that's the basis for most of modern encryption. It's also the basis of secure communications in general.
The hope for most of us, and there are some early results like this, is we'll be able to simulate things that we were never able to simulate before. And this could have applications in quantum chemistry and many different places.
Although we're still working primarily on the really basic science piece, we really feel that if this is going to happen somewhere, it's a place like IBM where it's going to happen. But we've also got to start thinking about how is this scaled up? What are all the other pieces that have to be brought to bear?
The quantum computing group is basically comprised of a bunch of experimenters with a few theorists, and we work very closely together in trying to build these novel devices to eventually scale towards a realizable quantum computing architecture.
We feel that the superconducting approach is going to be the best and fastest approach to getting there, but also things are happening fast, and a lot of things can change, and it may be that we undergo a change in our approach even at this point. There's a long history of superconductivity in IBM that some of this builds on, and I think the origin of our program came out of some of that history and the thinking of how to approach this problem.
Anything you can imagine can make a quantum bit not work well, and the whole point of what we're trying to do is build these guys on a chip, and you need to make them very, very well isolated from the environment in order for them to live long, and yet you need to be able to get in there and control them. The tool that we work these experiments in is a dilution refrigerator, and the dilution refrigerator gets down to 15 to 20 millikelvin. And it gets that cold because we need to be able to keep the quantum states very pure, and we want to get them into their ground state before we do any of our experiments.
We work extremely close together, the experiment and theory group. I will find myself sitting in the lab with the experimentalists and helping them analyze their data. I will also find myself having many discussions with them about experiments that can be done.
This, I think, more than any other thing I've been involved in, involves this incredibly strong connection between theory and experiment.
At IBM, since I started, we're seeing breakthroughs pretty regularly, maybe every couple of weeks. So it's pretty exciting. The biggest breakthrough we're actually having at the moment is we're pushing our ability to control these systems. When we normalize this to how fast they decay into the environment, we're pushing this right up into the very high nines. And if we get this to very high nines, like 99.99, then there's the possibility that very soon we'll be able to realize things like a logical qubit. And in principle, this is a qubit that never decays.
It feels very good to be on the cutting edge of this type of technology, because it's something which feels like it has a lot of potential. And knowing that the problems that are out there that you could try to solve with this technology are that difficult for classical computers gives us a lot of motivation to be working on this.
I think the thing that's really exciting right now is that on the experiment front, we're actually doing things that are making us think like, hey, this isn't 50 years off. This may be just 10 years off or 15 years off. It's within reach.
I see us building a quantum computer. It will take a lot of work, but I don't see anything that will stop us. We haven't worked out all the path yet, but we have an idea.